Welcome to NPTEL lecture, a basic course on electric and magnetic circuits. In this lecture, this is the last lecture on this 5th module on magnetic circuits. We will discuss some of the applications of magnetic circuits. Let us go to one application on lifting magnets. For that, we need to see what is the force of attraction between two poles of an electromagnet. So, this is an electromagnet having a magnetic coil with n number of turns, and we are providing a current I to this electromagnet, and let us we have an air gap, and this air gap. So, as per this right hand thumb rule, the flux goes in this direction as shown, and therefore, we consider the corresponding left side this to be north pole and the right side to be south pole of the air gap. So, let the air gap has an area of A g as we mentioned here, and the gap between these two poles north pole and south pole, that will be x. So, let the corresponding force of attraction between the two poles be F, there will be magnetic pulling between north and south pole. So, let us now we have an arrangement to quantify this for F like this, where we have a flexibility that this side south pole side can be moved left and right. So, that we can change the corresponding distance x. Now, to displace a distance d x to the south pole as we have marked here. So, this is the distance d x and this is about the x. So, the force against the pulling force which will have to exert external force, that becomes equals to F A into d x. So, energy per volume in the gap we have already known in our lecture 5 that while considering the half L I square and therefrom we derive the corresponding energy contained in the magnetic field. So, for the air gap this becomes equals to b square upon 2 mu naught, this per volume. So, into volume will be there for the total energy stored in that magnetic field. So, b square upon 2 mu naught, that gives us the corresponding energy contained in the air gap per volume. So, increase in the stored energy by this increment displacement of d x, additional displacement, that increment becomes equals to b square by 2 mu naught A g into d x, where A g is the air gap area. So, that leads to the corresponding equating the corresponding work done for displacement of d x. So, F A d x, that equals to the energy increment in the magnetic field in the air gap. So, that becomes equals to b square upon 2 mu naught A g into d x. So, that leads to an equation, the force of attraction between the two poles in the air gap equals to b square upon 2 mu naught A g. Once again, the force of attraction between the north pole and south pole, left and right side of the electromagnet becomes equals to b square upon 2 mu naught A g, where b is the corresponding flux density in the air gap, A g the air gap area, and mu naught corresponds to the permeability of free space. And we know here that the force of attraction becomes this, and the total energy contained in the air gap becomes equals to b square upon 2 mu naught, b square upon 2 mu naught into the volume of the gap. So, volume of the gap equals to A g into length of the gap L g. So, that is what the general equation for this. So, now with this idea we can calculate the corresponding for this electromagnet, the corresponding force of attraction and the energy stored in the air gap. Let us see this example. So, the magnetic system shown in the plot here figure here has a number of turns of 500, a current flowing in this I is 2 ampere DC current, width of the air gap is 2 centimeter, depth is again 2 centimeter, and length of the air gap, this length of the air gap is 1 mm only. Neglect the reluctance of the core, see here, neglect the reluctance of the core. So, the core part reluctance SC is 0, it means that there is no HL drop in the core. The leakage and fringing are also neglected. Determine the force of attraction between the between both sides of the air gap. So, what we say here, F A in the earlier derivation we see F A equals to B g square 2 mu naught into A g. So, for this requires B g, but B g equals to H mu into H, mu naught into H into H g, but H g here equals to, note we have H C L C equals to 0, as you have learned, as given in that reluctance of the core is neglected. So, that equals to S phi part. So, therefore, S C L C 0. So, H G L G is nothing but the corresponding MMF drop in the air gap, that becomes equals to MMF provided by the coil, that equals to N I. So, from this you can find out this H g. So, from the F g you can find out this B g, and from B g you can find out the corresponding F A equals to B g square 2 mu naught A g, and A g is here the area of the cross section of this. So, 2 into A g equals to 2 cross 2 into 10 to the power minus 4 meter square, and L g is given to be 1 into 10 to the power minus 3 meter. So, this data we can find out the corresponding F A, and we can find out the corresponding energy stored in the air gap, that becomes equals to the energy equals to B square B g square 2 mu naught into B g, the volume of the gap equals to A g into L g. So, that way we can calculate the corresponding energy in the air gap. So, this leads to us, as I mentioned, H equals to N I upon L and B equals to mu naught H. So, therefore, this F A equals to B g square 2 mu naught this, and this leads to the corresponding F A equals to 251.33 Newton. Similarly, the energy equals to B g square upon 2 mu naught B g, and that becomes equals to B g square 2 mu naught A g into L g, and this gives us the corresponding energy contained in the air gap to be equals to 251.33. Now, you see here this H g and L g, H g and B g we found out, and then from there you can find out the corresponding force of attraction between the two sides, and then we get the corresponding energy contained in the air gap to be 0.25133 joule. Now, this feature property of the electromagnet can be used as a lifting magnet. So, this is an electromagnet, and this is an iron piece. So, this electromagnet behaves like a magnet. So, when the corresponding current happens to be there, so you see here the current happens to be there, that means that the corresponding flux will go from the corresponding flux will be going from this side to that side, and therefore, this acts as a north pole, this acts as a south pole, and that is the reason the corresponding iron piece will be attracted to the particular magnet. Now, note that there are two air gaps here associated with this. Generally, the corresponding core MMF drop is neglected, reluctance is neglected. In that scenario, how does the corresponding magnetic pulling happens to be there? And you note that at each air gap the corresponding magnetic pulling happens to be F A, which we have already calculated, that equals to B square upon 2 mu into A g. So, that relation gives us the force at this point, and so also the force at this point. So, therefore, the corresponding force becomes 2 into F A. So, this becomes twice of the pulling force. So, the corresponding iron piece is exerted with a force of F A plus F A, that equals to 2 F A. So, see this example now. The lifting magnet system shown in the figure has a square cross section of A g equals to 6 into 6 centimeter square. The coil has a turn of 300 and a resistance of 6 ohm. The coil resistance is 6 ohm. Neglect reluctance of the magnetic core. So, that is the same, that the H c L c equals to 0, ampere turn in the core becomes equals to 0, leakage flux and fringing in the gap are also neglected. The air gap is initially held at 5 mm. So, this is a 5 mm air gap at both these sides. So, this is the scenario, and a DC source of 120 volt is connected to the coil. Determine I, the stored field energy, and the lifting force. So, what we say here, that again it is similar situation. We have this Ni that equals to our MMF, which gives us the corresponding Hg, Lg, and here we have 2 air gaps. So, this comes out to be 2 into Hg, and Lg is 5 mm here. So, substituting this value, we can find out the corresponding Hg. From Hg you can find out the corresponding Bg, the flux density, the gap, and then from Bg you can find out this corresponding Fa for each side Fa. So, the total force in the system becomes 2 Fa, and that becomes equals to 2 into Bg square upon 2 mu naught into Ag, and Ag is here is 6 into 6 centimeter square, that becomes equals to 6 into 6 10 to the minus 4 meter square. So, this gives us 2 Fa, and again the corresponding energy stored in this case becomes equals to the energy stored in these 2 air gaps. So, that becomes equals to V square upon 2 mu naught into the V into the 2, because the energy stored in the both sides of the magnet. So, this gives us the corresponding equation related to that the current here becomes equals to 120 volt supply, and the resistance is 6 ohm. So, that becomes equals to 20 ampere current, and because the reluctance of the magnet core is neglected. So, this whole of the MMF is confined to this here at the air gap this side and air gap this side. So, HGLG and HGLG here. So, as mentioned, this is 2 HGLG. So, that becomes equals, from there you can find out the corresponding B, and B comes out to be 0.754 Tesla. The Vg, the volume of the gap, that becomes equals to 2 times 6 into 6 into 6, that is a area into the 5 mm the gap. So, this becomes equals into 10 to the minus 7, 5 mm 6 centimeters 6 centimeters. So, that gives you 10 to the minus 7 meter cube volume. So, both volume 1 and volume 2 combinedly gives you this volume. Energy in the air gap, 2 air gaps, becomes equals to Bg square 2 mu naught into Vg. So, that becomes equals to 8.1434 joule, and the lifting force Fa equals to twice, 2 sides twice each of the force Bg square upon 2 mu naught Ag, that becomes equals to 162.78 Newton. So, this is a lifting magnet example case. So, once we have an electromagnet with a certain current, it can give us a force at both ends, and the corresponding 2 Fa can have a pulling to the magnet, pulling to the any iron piece or so, that can be used in lifting the iron or any such material in industry. Another example, the lifting magnet shown in the figure has pole pieces each having a cross sectional area of 25 centimeter square. So, the corresponding cross sectional area, the pole here again similar to that, having a cross sectional area of 25 centimeter square. So, this Ag equals to 25 centimeter square equals to 25 into 10 to the minus 4 meter square. The total flux crossing each pole is 250 microweber. So, flux is given to us. Determine the maximum weight of the iron plate that can be lifted by the magnet. Question is, determine the maximum weight of the iron plate, this is iron plate, that can be lifted by the magnet, neglect magnetic leakage and fringing. So, here also we say here that what is the corresponding weight of the magnet. Let us, we know that the corresponding Fa, total Fa which will be exerted on both sides, that becomes equals to 2 into the corresponding B square Bg square upon T mu naught into Ag, and the Bg is nothing but phi is known to us, phi divided by Ag gives us Bg. So, from Bg you can find out this corresponding this Ag is given to us, that equals to 25 centimeter square. So, we know this corresponding F value, the total force exerted on the iron piece which will be placed below. Now, we talk about here that what is the maximum weight the corresponding lift can successfully lift the iron piece. So, in that case let us say the corresponding mass of the iron piece, maximum mass of the iron piece becomes m1. So, the force on this m1 that becomes equals to the gravitational force becomes m1 into g. So, this maximum, this must be equated with the corresponding force which is available, that becomes equals to your F A which you have calculated here. So, from there you can find out the corresponding m1 which you can get. Below that all such mass can be lifted by the arrangement, and above that the corresponding magnet will fail. So, that is the optimum mass you can say that we are talking about. So, we see here that phi is given to us. So, B can be obtained phi upon A g. So, that comes out to 0.1 Weber per meter square, then F A equals to 2 into B g square 2 mu naught A g, because there are 2 air gaps here. So, that becomes equals to 19.999 Newton, and as I mentioned m 1 will be the maximum mass of the plate that can be lifted. So, that becomes equals to the weight corresponding gravitational pull downward will be m 1 into g. So, g equals to 9.8 meter per second square. So, then that becomes m 1 becomes equals to 2.03 kg. If you equate the corresponding 19.9, this becomes 2.03 kg. Therefore, the maximum weight the plate can lift will be 2.03 kilogram. So, these are some of the examples on lifting magnets which an electromagnet can contribute to this, typically in steel mills, and so it is being used. There are several other applications we can find in books and literature. We have already mentioned at the initial lecture about a motor case. So, this motor we know that if you can have electromagnet here, then a rotating a current carrying conductor in the rotor can experience a force. So, that is by the left hand rule. So, governing the left hand rule, the corresponding rotating direction can be obtained, and that leads to the production of torque and kinetic energy and the mechanical force developed in the rotor. Similarly, in case of generator which produces electric energy, electric power, it is output. So, in that case we have the right hand rule happens to be there. So, in a magnetic field, a rotating conductor develops a voltage, and that voltage can be connected to the outer wall for electricity supply, and so that is about the generator cases. So, typically in large stations, in thermal and hydro stations, we have large generators called alternators, and those use electromagnets to produce field or flux, and from there the rotating conductors gives us the voltage. We know the transformers all around you must have seen. So, transformer is also an electromagnet. So, typically a simple single phase transformer can have 2 coils. So, when coil 1 is energized with a AC supply, then we notice that there is voltage developed in the coil 2. Further details on the transformer we will study in the next module, and that is a special chapter on the transformer. So, we will discuss more on that in the next module. There are few more interesting applications also called magnetic levitation, maglev. Train in the train system it is being used. So, these are having electromagnets to levitate their rolling stock above the tracks, and they travel on instead of using wheels on the roll or so. So, in that case maglev or magnetic levitation, a floating vehicle for land transportation systems, it is a floating system supported by either electromagnetic attraction or repulsion principle, and it is less expensive to operate and to maintain, because it is there is absence of rolling friction in the system. So, these are several such applications you will find in the globe like China, Japan, and so. These are however, the investment is required because the rails are different. So, it is highly requires investment, large investment for this purpose. There is another applications which I like to highlight here. We call it shunt reactors used in high voltage electric power transmission systems to control voltage. Let us say this is a source supply system, and then we have a transmission line. We have a transmission line represented by this impedance, as we have seen examples in our AC system also while discussing AC system. So, there are loads connected to at this point, and suppose the voltage at this bus, that is V 2 is becomes higher and higher, and that goes beyond the limit. So, to arrest the voltage, to decrease the voltage, at that time the reactors are connected. The reactor is nothing but a shunt reactor connected in parallel. So, these are nothing but inductors, they are iron core reactors connected to this. So, these are generally in 3 phase systems available in the substations, high voltage substation. So, what happens that once you connect this reactor draws current which are lagging current, and then the corresponding current flows in the line. So, therefore, the corresponding V 2, this V 2 becomes equals to V 1 minus the corresponding inductor current I L into the Z line, and thereby more and the once we have this corresponding shunt current I L, then the corresponding V 2 becomes lesser and lesser. So, that is the results in the drop in voltage for the system, and it brings the corresponding voltage to the required level instead of in the case of the voltage becomes higher than the rated required voltage. So, this is one another application of electromagnet or inductor in high voltage system and so. So, we saw different applications of the electromagnets in this lecture, starting from the lifting magnet to motor, generator, transformer and reactors, and so we will find versatile applications in different applications. Furthermore, this study on our magnetic property of this electricity, we know that at the beginning we mentioned that a current carrying conductor produces flux around it, and thereby a flux linking to this conductor current results in an inductance and phi by I. So, with that property in a transmission system also we have different conductors, 3 phase system, 3 phase lines, each one carries a conductor like I A, I B and I C, 3 phase systems. So, each conductor carries current and they result in inductance also. So, therefore, while modeling these corresponding systems like that, we need to incorporate also not only resistance of the conductor, also the inductance property of the system. So, this is the last lecture on magnetic circuits. We will discuss in next lecture on the transformer. Thank you.